So I've shown you how to generalize notion of symmetrizing, anti-symmetrizing a function on a line. I've shown you how to do this whenever you have a cyclic group of symmetries, whenever the space can be divided in a bunch of copies such that by rotation you can go from copy to copy. So this is a discrete subgroup of SO2 rotations in a plane. To understand the general case we're extremely lucky, it suffices to understand symmetries of a triangle. If you understand symmetries of a triangle, everything else comes out. Everything else is just straight road from it. So now we'll discuss 6-element group that has, again, many names. In crystallography, it's called dihedral. Don't ask why. In combinatorics, it's called permutation. And in 19th century crystallography, it has 3 names. So dihedral, finite groups are dihedral called these, and this is the third one. Or it's like a cyclic group on 3 elements, but it has a reflection added to it. So it's bigger. And it turns out it's the same as permutation on 3 objects, which is the standard representations of symmetry groups, permutation group. So that one is much easier to draw. I have 3 pieces. There are 3 symmetry axes. And the easiest one that we are very familiar with is the one in which, for example, we take a billiard with 3 copies of a disc. And billiard doesn't have to be open, so maybe we make it look something like that. So it's a propeller which is symmetric in both directions. I can flip it, it still looks like itself. And now, fundamental domain is 1/6 of the world. I can take this neighborhood, and I can call it fundamental domain. And then if I flip it, I get this one. If I flip it that way, I get that one. If I rotate it by 1/3, I get that one. If I rotate it by 2/3, I get that one. So in 2 flips and 3 rotation, which is total of 6 elements, I can cover the whole space. It has a matrix representation that's not very illuminating. So, matrix wrap, which is what I just told you, is I have identity in plane, and then I have rotation by 1/3, either by 1/3 or 2/3, so that's cyclic group. But then I can do a flip. So, for example, in this axis, x goes to -x. X changes sign, but y doesn't change sign. It's a flip. And then I'll call that sigma. And then I can rotate and flip, or flip and rotate by 1, or I can rotate by 2 and flip. And that's the whole set of 6 elements. So let me see, maybe I can be more. So let me call this operation, I'll use little letter A, meaning I flip around this axis. Then around this axis, I'll call it B. And around this axis, I'll call it C. Then I can rotate. So another list of elements is, I say, group C, dihedral group on 3 elements, has identity. Then it has 3 flips. And then I can rotate. So I can rotate the whole thing by 1/3. So D rotate clockwise, I'm just following some, random notation from a crystallography book. And then the last one I'll call F because this is identity. And you rotate by 1/3 anti-clockwise. Then you build multiplication table always. And that defines the group in abstract way. So you find out that A square equals B square equals C square equals identity because flipping twice is the same thing. You find that rotating clockwise twice is the same as rotating anti-clockwise once. And the same going the other direction. Then you find that rotating 3 times is identity. Rotating 3 times in other direction is also identity. And then there are actually few things that you have to compute. So for example, if you flip and rotate by 1/3, it's the same as flipping around the B. So let's see where we understand that. So we flip, so this thing comes there. And we rotate by 1/3, and I don't see it, but hopefully you see it. It's same as using B. So you fill out this table. So you get something that looks like that, I'll leave it to you as an exercise. And right here, the inverses. And you just start filling it out. So these 2 rows are trivial because you're doing it by identity. Diagonal is just diagonal. And you fill it out slowly. So that is abstract description of the group. And now comes the part that I really, it would, I'm trying to be as gentle as possible, but it would take me 2 lectures to get the whole theory, and it's really easy to learn it yourself. If you read it, so just explain what the theory does. And, you check the steps. So what the theory does, it says, in general, E-reps are given by projection operators if we are looking at a function and decomposing that have the same structure which I've written already. You average over the group, so you always average over the group, and then you compute the character of the group element in a given representation. And you apply the group operator. So the key object is the same for all finite groups. And for compact Lie groups, this will be replaced by an integral called hard integral. But you'll always be averaging over the elements. And you will be weighing each with the character of the representation. Now, through a century, people have developed very pretty rules how to compute characters. So you actually do it mostly by thinking. And it's very cute. And characters, you find out in this higher dimensional setting, a character is a trace of the representation, irreducible representation of G, so that sounds like something difficult to compute, but the way you actually compute characters, you use very simple sum rules. For example, the dimension of the representation, so these now have dimensions larger than 1. Dimensions of the representation square have to add up to the size of the group. Looks like nothing, but actually is a very strong constraint. So in this particular example, what will happen for the 3-disk problem, or the triangle problem, there are actually 3 E-reps And to understand this number 3, you have to learn about classes. So there is some part of group theory that I hope I don't do, but I'll think about. Maybe I'll do it on Thursday, but it's really basic stuff. And they have to be of dimensions that they add up to 6, because there are 6 elements. So it turns out only possible dimensions you can have is 2 one-dimensional representations plus 1 two-dimensional representation squared. That'll give me 6. So that this kind of thing tells me about dimensions of representations. And then you'll do a character table, and there'll be 3 kinds of things that appear in the character table. There'll be identity. Then there'll be a class of objects which are flips, and they'll all contribute in the same way. They're called the class. There are 3 classes. And there are rotations. So that really simplifies your life. And it has to do with symmetries because you know in your heart that this operation is same as this one, and same as this one. So there's, all these flips should be somehow the same. There are 3 of them, and characters are beautiful because this particular formula says that evaluated for all 3 flips, because of this trace, you get the same character, because they're related by similarity transformation, just by coordinate. And qualitatively different is rotation. That cannot be same. They're 2 distinct rotations. And then they have some convention. The most symmetric thing is called A1 since 19th century. Then there is one that's asymmetric, 2. And then there is a 2-dimensional representation that appears twice. So what these projection operators do for you, they look very abstract, but what they do is they take a 6-dimensional space, which is full of all your matrices that permute 6 elements are full of entries. And it writes it as a block which is 1-dimensional, call A1, 1-dimensional, call A2. And then there are 2 copies of the 2-dimensional representation. So what the theory of group characters does is it diagonalizes representations of any finite group. And it tells you for finite groups there's always finite number of representations. And the projection operator, these numbers are same no matter what you act on. So here I'm acting on a triangle. But I could have a Hamiltonian problem, these 3 positions and 3 momenta and some potential that's symmetric under rotation. And it will also work for that. So these numbers are always the same, and this is particular operator on particular realization of your physical system that has this abstract group. Come in. Done with this.